Welcome. In this lecture, I'm going to talk about downhole networks and inflow control. So many times wells can be quite complex downhole, and I will go through some examples to show you this, and then to use that as a base for the discussion of downhole networks and inflow control. So the first example I have here is a multilateral well, in which we have a common vertical wellbore, but then we have three branches that they might be going through the same formation just to increase the drainage area, or they might be producing from different reservoir, from different formations. And effectively, it's like if you have three wells into one, so then you have like 3 times the rate, might be, and then that causes that you will have higher revenue, but you also add a bit of complexity that can cause that you need maybe more frequent intervention, or that is more complex to operate this well. But it might be, for example, that is a reservoir which is a heavy oil reservoir, that if the production of only one branch won't be enough to cover for the cost of the well. Okay, so then you need to drill three. Another example, and here we have a common point, which we say, well, this is the flowing bottom hole pressure, that where all the points are, all the branches are commingling and going forward. Okay, I'm assuming that this might be the point, but I might have also a flowing bottom hole pressure for each one of the branches. Okay, another option is another scenario is multi-layer wells. Here, for example, I have two layers, one shallow and one deeper, and then I have perforated the casing in these two locations, and then I have the flow of two layers flowing up. And then in this case, I can produce these two layers only with one wellbore and the bottom of the tubing here. So to analyze these cases, I use a technique, or this is essentially what I call a downhole network, because it's not only one flow path that I can take from the surface. For example, I go from the separator, I go from our wellhead, and I go to the reservoir pressure, but then I have actually essentially two, in this case, I have two reservoir pressure. So I have like a path that is split into two. Or if you see it from the other side, you have commingling streams that are merging and then are going up. And here I have something also similar here. In this case, I have three. Okay, so this is what I call a network, in which I have uh, several flow paths that are usually commingling together and then going to surface. Okay, so this typically I can use a network diagram to analyze this. So that's what I'm going to show under this square here. So consider we start from the wellhead, and then we know that in between the wellhead and this flowing bottom hole point, I have a tubing. Okay, so this will be my tubing, and I'm missing here the name. Tubing performance relationship. Okay, so I have essentially the pressure drop along the tubing all the way to reach to flowing bottom hole point. And then from here I have, I'm going to assume that that pressure will remains constant. The pressure drop along this wellbore, there is almost no pressure drop. So then essentially what I have from there right away is the inflow. Okay, and I have three different inflows that represent the three different branches, and then all of them, in this case, they reach to the same reservoir pressure. But it could be that if I'm going to another formation, then this will be the reservoir pressure will be different. Okay, so this is a network diagram, and I can use it essentially to solve and to estimate the well performance. Okay, so essentially here I apply a system of equations. I have here this TPR equation. I have one unknown and the rate, so two unknowns. And then here I have the IPR for each one of them, in which all of them have two unknowns, the pressure and the rate. Okay, and then finally I have a mass conservation equation that says that the sum of all of these rates is equal to the rate going up. So then I can solve simultaneously all of those equations and then find the results, the pressures and the rate. Sometimes I might have some cases in which it's a bit more complex. For example, the production, if the two branches are very close to each other, then the production of one is affecting the production of the other. Okay, and in that case, these two, for example, these two IPRs are going to be coupled. And in that case, it's not so simple to use a network analysis, starts to become very complex. And then what I might need to do is to use a reservoir simulator. might be a more suitable option. Okay, let's go now to this case that we have here. Okay, in which I have made my equivalent network diagram. I started from the wellhead, and then I know I have the losses in the tubing. I make it as a box, call it TPR, and then I reach here the flowing bottom hole pressure for layer 1. This will be my layer 1, and then I have that PWF1. And then from there, I have to go using an IPR equation to reservoir pressure 1. So that's this box that I have here. Okay, and then I go from flowing bottom hole pressure 1 to bottom hole pressure 2. I have casing flowing the casing, so I call the casing performance relationship. And then finally here again I have the same thing, an IPR2 all the way to PR2. Okay, so again making this diagram and applying it at a certain point in time, having the values of the IPR and the rate and the characteristics of the tubing and the casing, so then I can find out how much rate is being produced from the well and how much is coming from each layer. Okay, apply this equation, this equation, this equation, this equation, and then solve all of that simultaneously. But sometimes we can also apply network theory also for cases that are not so evident, or it's not so evident that there are networks. For example, let's consider the case that we have looked at before. It's a horizontal oil well with an underlying aquifer. In this case, we have a horizontal well in which we have, in this case, I have made it open hole, and then I have is completed in an oil layer, and then below I have an aquifer layer. So we know that the pressure inside the wellbore typically is going to change. It's going to be higher at the toe, and then it's going to be lower at the heel. Okay, so that will be that will cause that the inflow, the oil coming from, if I plot here, some oil coming from the influx of oil, this profile is not going to be constant. This is what I'm showing here. This might be some configuration in which I have very low values because that pressure is very high, but then when I reach the heel, then it's going to be increasing. So in this case, the influx is not going to be very uniform. Okay, and that might cause that essentially what I have, for example, is that the water cut in all of these sections of the well will be different because, for example, here I might have production of water in towards the heel, but then towards the toe I might not have any water at all. So it essentially behaves like two wells, two different wells. Another option might be that I have a well in which I have a distribution of vertical permeability that looks like this. So I have some streaks of vertical permeability here, for example, and here that are going to cause some coning, and essentially those regions are going to behave in a different way. Okay, so one way I can analyze this complex configuration is while using also a downhole network, an equivalent downhole network. So what I do is I try to split this into sections. Okay, so let's see our equivalent network that we had made here. So we have said the flowing bottom hole pressure is the point that is closest to the heel. Okay, then I have from that point up, I have a TPR, tubing performance relationship. Okay, all the way to reach to the wellhead pressure. And then I have divided my well into three different inflows. Okay, so it's like I have made here 1, 2, and then maybe 3. Okay, so I have 3 points in which I'm saying that this is representing that section, that section. So you see here I go from from PR, then I have an IPR for 3, and then I reach some wellbore pressure 3. Then I have a pressure drop along the wellbore that will reach to wellbore pressure 2. And here I have again another PR, and then I have an IPR, an equivalent IPR, and then the same thing all the way to 1. Okay, flow through the wellbore, then an IPR going here, and then finally I have a pipe going to PWF, from PW1 to PWF. Okay, so if I can apply also network to this case, what you might not think that this is a network. Okay, but if it's important to capture the heterogeneities that I have in the wellbore. So now talking about control. So for example, in this case, it might be that the branches, if they are very similar, it doesn't matter to be producing all of them at in the same way. But if they are very different, for example, you might say that this branch is well closer to the aquifer, and then it might have more prone to coning, or this branch is closer to the gas layer, so then it's also more prone to gas coning. So then I want to be able to control how much is coming from each one of these branches. Okay, so an approach for that is, for example, if I'm going to make it very simple, put it like a valve, a control valve. We're going to see now how these valves look like, but essentially I put a control valve in one of these branches, in each one of these branches. So then if I'm getting more water from one of them, I can close it. Or then if I'm getting, for example, more gas from one, I can close it such that I guarantee that I'm getting just oil. Okay, for this case, it's one typical problem that I have in this case is that typically I have one layer which has high storage capacity but has very poor productivity. And then I have another layer which is very highly productive but has low storage capacity. So what happens if I produce together these for some time, I'm going to empty the small layer and the big layer is still producing. So what happens is that sometimes I get actually a backflow and the small layer is actually stealing production from the high storage layer because that one is already depleted. Okay, so to avoid such a situation, I can do the following. So in this case, I have decided to make a more complicated completion. I make a liner or tubing. I simply extend it. Okay, put some packers to isolate each layer. I don't want, to have flow between the layer through the well. Okay, and then I put this blue element, which is some sort of control element, which I might control it. It might be something that I actively control, or might be something that is simply fixed at one position. Okay, but essentially what you do is that you have first flow from the formation to this annular space, then flow from the annular space and into the tubing through that element, blue element, that is essentially to control how much is coming in. Okay, and you do the same thing here. And this might be similar or might be very different. At least it gives you the flexibility that you can do different control for each one of them. Okay, so but you need packers to isolate that, and also you need that control element. Okay, let's go. What can we do in this case to improve the situation? We want the drainage to be uniform, not to have these peaks. Okay, we want this essentially to be uniform. Okay, so let's look at that case. What can we do there? Okay, so essentially what I have done, I have again split the wellbore into sections here, like I have 3 sections in which I have flow, and then I have added some sort of control element. Okay, for that I have run a liner, then I have put packers to put several sections. I might have here, I have just put just 3, but I might have quite a few in a long horizontal wellbore, and then I call this point the last point, flowing bottom hole pressure. So essentially the strategy before, remember that our pressure distribution was something like this, okay, very varying along the wellbore. Okay, what we want to do is to put all of them at the same level, at the same pressure. And the easiest is not to lower this down. It will be ideal if I can lower the pressure at the toe down the same level as the heel, okay, but then I will need to use some sort of a pump to reduce that pressure. Okay, but the easiest is to simply to increase the one at the heel to simply to increase that pressure. And for that is like I have to create an additional pressure drop to put everything together. Okay, here for example here, well, there is not much I have to drop in this location, but here I have to drop quite a lot, and here is where I have to drop the highest. But by doing that, putting that pressure constant, then I can ensure that the influx is constant. Okay, in the case that the permeability is completely uniform. Okay, if I have these high streaks, then that will not be the case. Okay, so that's how I achieve it. Okay, by using these pressure reducers, okay, or elements that cause pressure drop. And I will have to put this one very open, this one a little bit closed, and this one very closed. Okay, such that the delta P has this profile. So let's see how the equivalent network will look like that I can use to analyze that case. So it's very similar to this one that we had before, but now we have one additional element between the wellbore pressure and the formation, which is this inflow control. Okay, so I have reservoir pressure, the IPR for that section, and then I have the annular pressure that before I didn't need to distinguish between the wellbore and annular pressure, and then go inside the liner pressure. Okay, wellbore pressure 3. Then I go circulate through the pipe, and then I reach the other point, which is here, and again PR, IPR of section 2, P annular 2, go inside, wellbore pressure 2, and so forth. So simply by using this diagram, then I can start to design my wellbore, and then I can decide, well, what can I do to make these rates that come from each one of these sections to make these rates uh, the same. Okay, if I want to make a Q01, Q02, and Q03. Okay, so for that it's very useful to have this network diagram. So let's go now to how this inflow control looks like, how this equipment looks like. And we are going to try to go through one of the simplest and then start to increase complexity. So here we have a sliding sleeve. And we have two parts, so these are connected to the liner or to the tubing, this part. Here we should put, let's put the open hole or the casing. Okay, we have a packer here. And here we have our, if it's open hole, if it's a, or it's a casing, and here we have someplace the influx. Okay, so we have two parts. We have one outer part which is fixed, and then we have this red part which can move. Here it can move through three positions. You see equalizing, close, and open. And you see that the way that the fluid has to flow from the formation annulus and inside this liner is through these holes. Okay, but then to do that, then these holes has to be aligned with this big hole. Okay, you see here you have some black things, that these are the seals. So this avoid, when it's in this location, well, it can only go through this small port. Okay, so if you want to have a big flow, then you have to move this red part back, so these two are aligned, and then you will have flow into the liner, and then going, if you have wellhead, it's going to flow through that, the wellhead through in this location. Again, this is usually I can do shifting. I have to put some element inside. Some it can be, for example, if I'm in a horizontal well, I can use a tractor, or I can use a slick line. If I'm in a vertical, if this is located vertically, oriented vertically, but then I have to shift it, move this one to the right or to the left to achieve what I want. I might have several positions, not only open and close, but I might have something in between. Okay, I might have some holes like this one, which is a bit smaller. Okay, that produces some sort of pressure drop. Another type is this inflow control device, ICD, and this is simply opening which has a fixed, is fixed. The opening has a fixed size. Okay, so for example, here you see you have the flow coming from the annulus, coming through a screen that is filtering, for example, sand, taking out sand, and then it's flowing along this annular space, and then you go through this opening, and here you induce some pressure drop, and then finally you go inside the liner, and then you go up to the well. Okay, so this opening is what if I need, going back to our example of a horizontal well, if I need a big pressure drop, then this opening will be very small, but if I need a small pressure drop, then this opening will be almost non-existing. Okay, will be simply free flow. But that's how I can regulate how much is going through that. Okay, and that is an inflow control device. They call it passive inflow control because simply it's fixed opening, and then you cannot control it during the life of the field. Simply you have to say that this is going to work for all the life of the field. Then we have another variation in which I want to control actually actively during a matter of months or days or during the life of the field. I want to control the opening. And also one thing, I don't want to do like this sliding sleeve that I will have to do some intervention in the wellbore and move this red part. Okay, so for that we have inflow control valve, ICV. in which looks a bit something like that. Here you have the tubing is connected here, and this part is fixed, the yellow part. And here you have this part which is moving, this black or dark gray. Okay, and this uh, uh, more light gray, these are the packers, so not the packers, the seals. Okay, so what I have here, this is not the seal, but this is kind of part of this structure. This part is moving up and down, this dark gray part. Again, here you have two hydraulic lines essentially that are used to do that. Okay, so when the blue one, you push fluid through the blue one, then this is pushing everything down. And when you're pushing fluid through the green one, then this is pushing this up. Again, you see here that it has holes and they're aligned with these holes. But then if I push with the blue one, it's going to be closed because then the holes are going to be further down. And what is going to be aligned is going to be simply a blank, okay, no flow. Okay, here you have the open and the closed position. So this is what is called an ICV, and I might have several more positions, not only open and closed, but I have something by changing the number of holes, I can have something in between. 20% open, 50% open, 80% open. Okay, one complexity we have to take into account, or let's see what happens if you have several, like in this case, I have several regions where I want to make inflow control. Okay, here I had 1, 2, 3, for example, and then I have one to do inflow control valve with all of them. So see how it looks like. I have a hydraulic line for each one of them, okay? And in this case, I don't need, because here you need two for each one of them, but I need here just one return for all of them, which is the green one, okay? So it's actually, you have to, one thing is that these hydraulic lines have to go through the packers that are separated each region. So for the one closest, for example, if this is the toe, for the one closest to the toe, then it will have to go through all the ones that are until you reach the heel. Again, then until you go up to the wellhead. For the one that is closest to the heel, then you only have to go through one packer or two packers, and then you have to go up. But then this is a hassle and it can be quite complex to run this into the wellbore because you have to make sure that everything you run it goes, is connected properly and going through the packer. Okay, but in this case, you see, I don't need, if I have um, three, for example, if I have three ICVs, you don't need to have 6 lines, but then you need to have only 3 plus 1, so 4. Okay, so you don't need to have 2 lines for each ICV. Okay. And here you see at the top that creates also some issues, not only that you have to pass the hydraulic lines through the packers, but also you have to pass it through the tubing hanger. Okay, so you see here the line comes along the tubing, and then you need to have a port in which that hydraulic fluid is is connected to the surface, because remember that's what we need to push hydraulic fluid on one side and return it through the other, and then vice versa, just to be able to move this ICV. Okay, then we have some other approach in which we, to avoid all of this complexity control from the surface, we try to them to act somehow autonomously, that we try to sense what is the phase that is flowing and try to close or open depending on what it is. If I don't want water or I don't want gas, so it's going to close. So this is another technology called autonomous inflow control valve. So I don't need the hydraulic lines. And here you see it has this moving part. This is the wall of the liner, and this is this moving part which is in green. So it's open for oil, closed for water, and closed for gas. AICV. That's from a company called Inflow Control. So here you see one example of a completion. This is of Troll, and you see how the wells are. You have here 3 branches. You have an open hole completion. You have swell packers. You have a sand screen. Okay, and then inside you have this autonomous inflow control device. Okay, this was an earlier generation of the one that we have seen up here. Okay, so each one of these sections, you have the packers, and each one of these sections have these valves. And here at some place you see a flow control valve, which is essentially like an ICV, inflow control valve. They call it flow because it's not anymore in the inflow, but it's essentially in the main wellbore. Okay, so it can be quite complex, and here you see actually all the hydraulic lines, all of these that are blue, green, yellow, all of these are going to all the different things that need activation. Okay, the autonomous inflow control device, they don't need activation, but this flow control valve, they need activation, and you have some more things that need activation. Okay, that need and then just to finalize, I want to show you how packers, what kind of packers are used. So typically for open hole, but can also be for closed hole, we use two types of packers. Inflatable packers, in which we use some fluid to inject and to blow it up to increase the size, and then it makes contact with the outer wall. And this can be used when there is not very smooth the surface, like for example open hole, or also when there is a big difference, so it needs a huge expansion. Okay, you have also swellable packers in which you wrap some rubber around the pipe, and then simply with the contact with, sometimes it's with water, sometimes it's with oil, it swells, and then it increases its size significantly until it touches, and then it simply blocks it, it becomes stuck, and then that's how you block the space. There are some other types of packers that are used, but especially in case hole, because these are need first small tolerances, small space between the packer and the wall, and also they need it to be smooth. So this has to be usually with cased hole. Okay, like you see here, and essentially is that you squeeze, you pressure, or you squeeze this rubber from the top and from the bottom, and then it expands, sticks out, and then it touches the wall, and then that's how it makes the seal. Again, for that we usually it's a bit complicated how it is done, but you essentially have to compress from the top and from the bottom, and from that you typically use these slips that essentially they bite into the wall and they are fixed. You fix one part in place, then you squeeze, and then you fix the other part in place, such that they become this sticks out and then it becomes activated.